Hello and welcome to the CompTIA Cybersecurity Analyst CySA Plus Certification Study Guide. In this video, we will discuss Chapter 8.3, Managing Vulnerabilities. After vulnerability scans have been analyzed and the vulnerabilities prioritized, the next step is to manage the uncovered vulnerabilities. Managing vulnerabilities involves using controls, patch management, configuration management, attack surface management, threat modeling, and governance. It also involves consideration of the advantages of advanced vulnerability scanning techniques. Please like, subscribe, and leave a comment. Using controls. A security control is a safeguard or countermeasure employed within an organizational information system to protect the confidentiality, integrity, and availability of a technology system and its data. It attempts to limit exposure to a danger. Cybersecurity controls play a key role in a cybersecurity strategy. This is illustrated in Figure 8.3. Categories of controls. There are three broad categories of controls: managerial, operational, and technical. Managerial are controls that use administrative methods. An example is an acceptable use policy that specifies users should not visit malicious websites. Operational are controls implemented and executed by people. An example is conducting workshops to help train users to identify and delete phishing messages. Technical controls are incorporated as part of hardware, software, or firmware. An example is a Unified Threat Management (UTM) device that performs packet filtering, anti-phishing, and web filtering. At a granular level, there are specific types of controls that are found within the three broad categories of controls. These include compensating controls. A compensating control provides an alternative to normal controls that for some reason cannot be used. Corrective controls. Corrective controls are implemented after an incident has occurred to minimize damage, facilitate recovery, and repair weaknesses. Deterrent controls. A deterrent control attempts to discourage security violations before they occur. Physical controls. A physical control implements security in a defined structure and location. Between the three broad categories and the granular specific types of controls, there are three classes of controls. Preventive controls. A preventive control works to prevent the threat from coming in contact with the vulnerability. Detective controls. A detective control is designed to identify, log, and alert a threat that has reached the system. Responsive controls. A responsive control is designed to launch remediations to counter adverse events. Examples of technical response controls include updating a system after a software vulnerability has been uncovered, quarantining a computer after malware has been identified, or shutting down a process after malicious activity has been exposed. Detective controls are considered a prerequisite for establishing responsive controls. That is, the security issue must first be identified before it can be remediated. Once identified, a response can be activated to respond to the security issue. There is no universal agreement on the categories, classes, and types of controls. Some classes are listed as types of controls, while types of controls are listed as functions of controls. On some occasions, controls are presented as functions that have types. Additionally, other control types such as recovery controls, measures used to restore a system to normal operations, can be found. Patch management. As previously noted, not all vulnerabilities that receive a high CVSS score must immediately be addressed. Rather, depending on multiple factors, risk score, recurrence, context awareness, and weaponization, to name a few, there may be deviations, exceptions, from a policy of strictly pursuing all remediations based only on a high score. However, one category of vulnerability that is always of high priority is software that is out of date and is missing software updates. Over time, the responsive controls that address out-of-date and vulnerable software have proven to be one of the, if not the, most important vulnerabilities to address. In addition, it is often the easiest, quickest, and most economical approach, and generally will address a high number of exposed vulnerabilities. Early operating systems, OSS, such Microsoft Windows, Apple macOS, and Linux, were simply program loaders whose job was to launch applications. As more features and graphical user interfaces, GUIs, were added, OSS became more complex. Today's Windows 11 is estimated to have over 50 million lines of code, Linux Debian has 68 million, and Apple macOS may have upward of 86 million. In contrast, Microsoft's first OS Mississippi, DOS v1.0, had only 4,000 lines of code. Due to the increased complexity of OSS, unintentional vulnerabilities were introduced that could be exploited by attackers. In addition, new attack tools made what were once considered secure functions and services on OSS now vulnerable. In order to address the vulnerabilities in OSS that are uncovered after the software has been released to the general public, as well as to provide ongoing additional features, OS vendors deploy updates to users' computers through an automatic online update service. The user's computer interacts with the vendor's online update service to receive the latest updates. Patch management involves installing and managing these software security updates, patches, in a timely and effective fashion. There are several reasons why the timely installation of patches through patch management is important. Threat actors often watch for the release of a patch and then immediately craft an attack around the vulnerability that the patch addresses, knowing that many users and organizations are lax in applying patches. Or threat actors may reverse engineer patches to look for the vulnerability that is being fixed, and then craft a completely new attack based on that vulnerability. In either case, promptly installing patches is considered an important step to protecting a device. Effective patch management involves two types of tools to administer patches. The first type includes tools for patch reception, and the second type involves patch distribution. Some organizations find it necessary to test patches before allowing them to be distributed. Patch reception. Endpoint devices can be configured regarding the installation of patches. Prior versions of Microsoft Windows gave users several options regarding accepting or even rejecting patches. These options included download updates, but let me choose whether to install them. Check for updates, but let me choose whether to download and install them, and never check for updates. However, this approach frequently resulted in important security patches being ignored by users and putting their computers at risk. The patch update options for Microsoft Windows 11 are far less lenient, as shown in Figure 8. 4. Updates can also be delayed from 1 to 5 weeks. After that time, the updates will resume. Other options include setting a time range when the computer will restart after an update has been installed and optimizing delivery options that depend on the connection type. Apple macOS has similar features. Users can receive a notification that software updates are available, choose when to install the updates, or choose to be reminded the next day. Testing patches and patch distribution. Patches can sometimes create new problems for an organization, such as preventing a custom application from running correctly, and then requiring the patches to be backed out so the systems can be restored to their original state, also known as rollback. Organizations that have these types of applications usually first put the patches through a series of processes. The testing process is used to determine if the patch will adversely affect any customized applications. Once this is confirmed, validation process. The patches are installed, implementation process. Often, the installation is performed during a maintenance window, which is a scheduled outage of services over a digital platform in order to implement planned changes, upgrades, or repairs. How can an organization prevent its employees from installing the latest patch until it has passed testing and still ensure that all users download and install the necessary patches? The answer is to employ automated patch management tools. These tools are used to manage patches within the enterprise instead of relying on the vendor's online update service. Automated patch management tools typically consist of a component installed on one or more servers inside the corporate network. Because these servers can replicate information among themselves, usually only one of the servers must be connected to the vendor's online update service as seen in Figure 8. 5. There are several advantages to automated patch management tools, including downloading patches from a local server instead of using the vendor's online update service can save bandwidth and time because each computer does not have to connect to an external server. Administrators can approve or decline updates for client systems, force updates to be installed by a specific date, and obtain reports on what updates each computer needs. Administrators can approve updates for detection only. This allows them to see which computers require the update without installing it. Configuration management. Configuration management is a process for maintaining computer systems, servers, applications, network devices, and other IT components in a desired state. Configuration management involves establishing a clear approach to documentation, maintenance, and change control so that systems can be configured consistently and accurately across environments. In short, configuration management helps ensure that a system performs as expected, even after many changes are made over time. Configuration management databases, CMDBs, track individual configuration items, CIs. A CI is any asset or component involved in the delivery of IT services. The CMDBs store information about a CI's attributes, dependencies, and changes to its configuration that may occur over time. This allows IT teams to map and maintain the relationships that tie the CIs together. Using configuration management tools, administrators can set up an IT system like a server or endpoint and then build similar systems with the same settings. In addition, tools such as configuration assessments and drift analyses can continuously scan and identify systems that have strayed from the desired system state and need to be updated, reconfigured, or patched. Virtually every organization's digital footprint has expanded dramatically over the last few years. The major drivers of this expansion are the adoption of cloud technologies, the growth of remote work by employees, and the shift to digital transformation, the process of using digital technologies to create new or modify existing business processes, cultures, and customer experiences to meet changing business and market requirements. However, the expanding digital footprint has also widened every organization's attack surface. The attack surface is the sum of vulnerabilities, pathways, or methods that attackers will use to launch an attack, breach a network, or access sensitive data. According to one report, 2 out of every 3 organizations have seen their attack surfaces expand in just the preceding 2 years. Consider, for example, cloud computing. Whereas at one time an organization had its digital assets protected in a secure data center, today those same assets stored in the cloud not only make them vulnerable to virtually anyone with a web browser, but the protection of these assets relies heavily on the security of the cloud provider, who may or may not provide the desired level of security. This has created a new security defense known as Attack Surface Management, ASM. ASM is the ongoing discovery, analysis, remediation, and monitoring of security vulnerabilities and potential attack vectors that make up an organization's total attack surface. The goal of ASM is to lessen the number of points a threat actor can exploit, called attack surface reduction. Unlike some other security methods, ASM is viewed from the attacker's perspective. It identifies targets and assesses risks based on the opportunities they present to a malicious threat actor by mimicking methods and resources that they use. ASM includes the following security defenses. Edge discovery. Edge computing is processing data where the data is being collected instead of it being transmitted back to the traditional on-premises data center for processing. Because it is furthest away from the data center, it is at the edge. Edge computing can enable processing at greater speeds and volumes, leading to improved action-generated results in real time. Internet of Things, IoT devices, sensors, wearables like fitness bands, and even self-driving cars and autonomous robots are examples of edge computing. However, it introduces security risks. These devices are not fully protected by the organization's perimeter and may be subject to sustained attacks that can compromise not only the device, but also the secure network to which it is attached. Edge discovery is a component of ASM that takes efforts to identify these edge devices so that they can be recognized and protected. Passive discovery. Active discovery scans networks for new items, such as hardware devices or software applications. This can be done manually or through automated scanning tools that map out all existing records in detail. Passive discovery, on the other hand, operates more continuously with no manual intervention required. By monitoring historical activity patterns, it can identify any unknown devices connected to the network. Security controls testing. Security controls testing is the evaluation of security controls to determine the extent to which the controls are implemented correctly, operating as intended, and producing the desired outcome. As a part of ASM, security controls testing is an important analysis of overall security and if it functions as intended. Penetration testing. A vulnerability scan is a frequent and ongoing process that is automated to continuously identify vulnerabilities and monitor cybersecurity progress. A penetration test, on the other hand, is a single event often using a manual process in which the testers act like a threat actor, called adversary emulation, to find vulnerabilities to exploit. Both vulnerability scans and penetration tests are important to manage attack surfaces and uncover weaknesses to be addressed. Bug bounties. A common practice of large enterprises is to pay security researchers who uncover security vulnerabilities in their products and then privately report them so that these bugs can be patched before threat actors find them. This is called a bug bounty program. Organizations can use the data gathered from their bug bounty program to reduce their attack surface. Google, who started its bug bounty program back in 2010, pays from $100 to $31,337 per reported bug. To date, Google has paid out over $45 million in bounties and even maintains a bug bounty leaderboard hall of fame listing those who have revealed the most bugs. Zerodium, on the other hand, pays up to $2.5 million for information on a single vulnerability and does not reveal who supplied information on the bug. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. We will see you on the next one.